Welcome back to MC312 Thermal Fluid Systems 2. This is your second video for the Exergy in a closed system lesson. In the first video, which you should have watched before this one, we talked about the definitions and explained the concepts related to Exergy and really the dead state. This video will capture the second two lesson objectives. We'll be able to calculate the Exergy for a state as well as do a closed system Exergy balance. Important tools in the concept of Exergy analysis. Let's start with determining what the Exergy is of a closed system. The total Exergy of a system really refers to Exergy as an extensive property. So we'll use a capital E when we refer to this property, Exergy. And we're going to do it for a system at state I, so that's any old system you want to do analysis on. And it's a combination, essentially, of properties. It's going to have units of either kilojoules if you're in the SI system or BTUs if you're in the English system as your common energy unit. Exergy is related, obviously, to energy, but it also incorporates a consideration of what the dead state is. So we start with our difference between the dead state and our state in internal energy. We add to it the potential for boundary work, which in this case is a PV concept, and our volume is the difference in volume between the state of interest and the dead state. Now, that's a moving boundary work term, and so if it's positive, then the heat transfer term has got to be negative. We know the heat transfer term is going to scale with our temperature, T naught, of the dead state, and then the difference in entropy between the dead state and our state of interest. Now we have our kinetic energy term, so we have 1/2 times the mass of our closed system, and we get the velocity of our system of interest compared with the velocity of the dead state. Now, as a rule, we will assume this is 0 unless it's somehow specified. Otherwise, we shouldn't have that case in this course. And then likewise, we have mass, gravity, and a difference in potential energy. And again, just as we assumed that there is no dead state velocity, let's assume there is no dead state potential energy either. That'll be the definition of our dead state. Your textbook has this, equation 12.17. Or if you want Exergy per unit mass, so the intensive property of Exergy, that corresponding equation is in 12.18. So what is the Exergy change of a closed system? What we're talking about here is a process where you go from some initial state to some final state. We'll call the initial state state 1 and the final state state 2. So to go from 1 to 2, you literally just look at equation 1220b for the total Exergy change. And again, both of those cases have the definition of Exergy as we saw here on this slide. And you take Ex of I at state 2, Ex of I at state 1, and you subtract the 2. And so a few terms disappear and a few terms logically combine, as you can see in equation 1220b. So on this one, let's talk about the specific Exergy change. That's the total Exergy per unit mass. That's equation 1221. This first term here is the change in Exergy, as you can see, Ex2 minus Ex1. Then we have the net difference between state 2 and state 1 of the potential energy, in this case, the specific potential internal energy. We have our our dead state pressure times the specific volume difference. We have a temperature of the dead state, specific entropy difference, and that one's subtracted, again, positive for the work term, negative for the heat transfer term. And then we have the kinetic energy differences and the potential energy differences between the two states. Okay, so that's the Exergy change. It's really the application of this equation right here at state 2 less that same equation at state evaluated at state 1. But now what we want to do is talk about the concept of an Exergy balance. So let's start here with a quick reminder that what we're going to do is a substitution of the first and second law into that last equation, the equation right here, either on the specific Exergy change balance or we'll develop this now back on the total Exergy change, equation 1220b. And we'll look at that as a difference of the two. Now, as a reminder, entropy production is an expression of the second law. And so this reminder right here that the entropy production in process 1 to 2 is the difference in total entropy less the integration of the inexact differential of heat transfer, that's delta Q here, over the boundary temperature. So you integrate that term. If the boundary temperature is constant, of course, it can come out of the integral, and that becomes Q12. If it's not constant, then of course you have to integrate as a function, but it's a you then have a dependent integral in there, and a little bit more calculus is involved to get your terms. But you'll need an expression for the boundary temperature if it's not a constant. And I think it's always going to be a constant in this course. What do you get? Okay, EX2 minus EX1. That looks a lot like this last one, but what's going to change is what's on the right-hand side. So where's that? Sounds like the total Exergy change, and it is. The way we express it when we combine the first and second law is instead of terms of pure properties, we have it in terms of processes, right? So here's your inexact differential heat transfer again, where we accommodate the dead state temperature and the boundary temperature. Note if they're the same, and I didn't mean to do that, so we'll rewrite that. If they're the same and that becomes unity, of course, that term will disappear. I believe we want to look at these three grouping of terms. Absolutely. Those would be the Exergy transfer associated with heat transfer less the Exergy transfer associated with useful work. And so we have a subtraction here of both the work term and the moving boundary work term as well. That one's actually an addition, whereas that one's a useful work term subtracted. The last term is our Exergy destruction term. And together, this closed system Exergy balance is equation 12.25. But wait, there's a great resource for you. It's called the reference data card. If you look on the back side on the top left corner, you'll see this section here, Exergy as a closed system. Let's keep this handy when we need to do Exergy analysis for closed systems. Here's the first equation we developed. This is the Exergy compared to the dead state of any state, I, on a specific Exergy basis, on a total Exergy basis here in this case. Here's the Exergy change. That was slide number 2. Exergy destruction, work, heat transfer, all those terms there that we just developed in that slide there, and then combined with the definition of what each of the terms are for the Exergy balance using the first and second laws. This concludes the lesson 4 videos. I hope you